Okay, so now let us understand that how impurities in solids helps in controlling the mechanical properties as well as the electrical properties of a material. So we are going to talk about impurities in solids. Okay, we are going to talk about impurities. Sorry, impurities in solids. Okay, so you know any material cannot have a pure form. Okay, a certain amount of impurity will always be present in this material. Okay, so sometimes it is natural, sometimes intentionally some amount of impurities are added with the material to control its different properties. In fact, sometimes it is seen that if you are adding some impurities in the solids, its mechanical properties uh, are found to increase, right? And so we can say that the foreign atom or impurity will always be present, and some will also exist as crystalline material as a point defect. So okay, so these impurities sometimes can present as point defects, sometimes it can present as point defects, point defects in the material, right? And so therefore it is better to call this impurity added solids as alloys. Okay, it is better to call it alloys, right? It is better to call them as alloys, right? So if I consider, for example, silver, sterling silver. Okay, so sterling silver, if you talk about silver, only silver, uh, the pure silver is obviously corrosion resistance, but sterling silver, so this is an example of an alloy which is a sterling silver. Sterling silver, in this what we have is the 92.5%. We have 92.5% silver, and with this 7.5, rest of the 7.5%, what we have is copper. Okay, so in normal ambient environment, this pure silver is highly corrosion resistant, but it is very soft. So for ornament use, you can use it, and alloying this silver with the copper significantly enhance the mechanical property. Okay, and also corrosion resistance. So these alloys are prepared to for a different reason, mainly to improve improve mechanical properties. Okay, mechanical properties, to improve mechanical properties. Okay, and second thing which is also important is the to corrosion resistance, right? To resist corrosion. So corrosion resistance. Okay, So mainly these alloys are prepared to resist this corrosion and also to improve the mechanical properties of this material, right? Now, how if I am talking about the alloys, so mostly a metal will contain another metal, or it means we are talking about uh, one solid which will mix with another solid. So it is basically a solid it is consisting of both the solids, right? This is what we call solid solution. This is what we call solid solution. This is what we call solid solution. Okay, so how this solid solution are prepared, that is now we will see. Okay, so how the solid solution is formed, that is what is quite important to know. So the addition of impurity atoms to a metal will result in the formation of solid solution. Okay, but we it depends on the what is the impurity, what is the concentration of that impurity. So the solution, how the solid solution will form, or whether there will be a formation of solid solution or not, that will depend on the what kind of impurity we are going to add, what is the concentration of it, what is the temperature, etc., right? So mainly if we are talking about a solid solution, so it will have two components, right? A solid solution will have mostly two components. One will definitely will be the solute, one will be the solute, and the other component of it will be solvent, right? Will be the solvent. Because see, if you are talking about a, let's say we are talking about a liquid solution, in case of a liquid solution, then both the component are solute and solvent, both are liquid, right? Both are liquid. But here, as we are talking about a solid solution, so here both solute and solvent both will be solid, right? So that is a little bit difficult. So what is solute, you say? So solute nothing but the foreign atom, the uh, which is going to be added with the host atom. So this is the foreign atom, right? And or you can say this is the uh, I mean solvent is, so let me just which will be dissolved in the solvent. Okay, so like in this case, if you have a, you may have a solid which is dissolved in a liquid. So generally, so suppose if you have some amount of sugar which is let's say, so suppose you have some amount of sugar which is added with the water, right? And then you form a solid solution, liquid solution. Here sugar is the solute, okay, and water is the solvent, right? So solvent is represent what? Solvent is the element or the compound that present the greater amount in the material, right? Right. And solvent is the foreign atom which will be added to the host atom. So solvent is basically the host atom, host, right? So solvent is the host, and this is the which is coming from the outside. So this is coming from the outside. So that's why we said this is a foreign atom, and this is the host. Okay, this is the host, right? Now, when we call that a solid solution has formed, okay, so any amount is not possible, any size of the solute is not possible. There are so many restrictions which is there. to form a solid solution. That is what we are now going to talk about. So we can say that a solid solution is formed when the solute atoms are added to the host material and the crystal structure is maintained. Okay, so now I am talking about the criteria, or uh, basically criteria for formation of solid solution. Okay, so now we are going to start talking about what is the criteria. I mean that what condition and what criteria it has to maintain to formation for the solution. So first we'll say that the to form a solid solution, the whatever the solid atoms you are adding into the host material, so solute will be added to the solute atom will be added to the host material, but the crystal structure of the host material should not change. The crystal structure of the host material should not change. So the first criteria is that the the crystal structure of host will remain same, right? So if you have a host, let's for example FCC, it has to be FCC, whatever the amount you are going to add as a solute, right? Or if you suppose if it is a BCC, so it has to maintain its the same crystal structure, that should not change, right? So this is the first criteria. Second criteria is, so the second criteria is whatever the solid solution is prepared, right? It has to be homogeneous. It has to be compositionally homogeneous. It has to be compositionally it has to be compositionally homogeneous. So in that case we can actually draw the analogy with the liquid solution. So suppose if you have two liquids, okay, for example you have water. So suppose if you have water and alcohol, okay. So suppose if you have water and alcohol which are combined, so a liquid solution is produced as molecule intermix, right? And its composition is homogeneous throughout. So you really won't make any distinction that which part is water, which part is water. So this is, you can say, this is a completely homogeneous. This is completely a homogeneous solution. And you understand what is the meaning of homogeneous solution. So whatever the direction you will go, you won't see any difference in the property of this solution, right? So this is an analogy where we are talking about both are liquid. This is also liquid and this is also liquid, right? But it, now it in this case it may appear little easier because both are liquid, it can easily mix together, right? But now if you remember that we are talking about two solid and which has to be mixed homogeneously, that is a difficult task. This is really a difficult task, and therefore there has to be so many things which we need to consider, right? So a solid solution is also has to be compositionally homogeneous. So uh, it's composition wise, each and every part of the, so suppose if you have this, suppose this is a material where you have set some amount of this is the host atoms, right? Right. And suppose if you have some foreign atoms which are also sitting somewhere like this, and crystal structure is not changed, right? Crystal structure is not changed and it is maintaining. So you can see at each and every part of it, it is a homogeneous structure. It is homogeneous. So this homogeneity has to be maintained everywhere. So any part of it, it is compositionally homogeneous. So it is, let's say, compositionally homogeneous, that we you can see from this figure, and also the crystal structure, whatever the crystal structure of the host material, that has to be maintained. Then only you can say now yes, a solid solution is formed, right? Now, in doing so, there are two way by which that can be possible. Which possible? That solid solution formation is possible by two way. What are these two way? There are, so here you can see here we talked about two things. Which one is the host atom, right? Host atom and the solute atom. Okay, so host atoms and the solute atoms. Now, what are the criteria that they will be accepting each other? That now we are going to talk about, right? So it means the impurities or foreign atoms, whatever, which are uh, intentionally added to the solid solution, there are two types. Okay, so the formation of solid solution. Okay, so two ways, two ways they will form. There are two ways this solid solution will form. So one is called substitution, okay, where solute replaces or substitute the host atom. So one is called substitutional. One is substitutional, and the second type of the or I can say the second way of forming a solid solution is the interstitials. Interstitials and substitution. This is not required. Yes. Fine. Now, the figure already I have drawn earlier. So suppose I have this kind of arrangement of atoms as the host. So let's say this is my host, right? And if I draw a realistic picture, so you need to understand that they are actually bigger than this. So, okay, let me just draw a realistic picture. What I mean by the realistic picture is if I am talking about metal, so they are they are very closely spaced, right? They have a close spacing, right? So if I just, so I have to take them a little closer. Okay, so I have to make them little closer. Okay, fine. Fine. So suppose this is my host. So this is, let's say, my host, and I'm going to put some substitution. So I am putting some substitution into it, and let's say I have this. This is the atom which I have substituted. Okay, this is the atom. The blue one is the substituted. So this is an example of an substitution. Okay, so this is an example of substitution. Okay. Now suppose if another atom, okay, if suppose another atom which is a very small in size, which is very small in size, go and sit here, somewhere here, okay, in between, in the interstitial. So that will be interstitial. That will be inter. Okay. So one of the kind which will not replace the host atom but will sit or the fill the void or the interstitial among the host atoms. And there is another way of adding the foreign atom as the substitution. It will go and substitute the host atom, right? But the question is now, what is the acceptable size of this substitution, the atom which is being substituted, right? So that is a very important question. So there are some several features, several points of the solute and solvent atoms which will determine the degree at which the foreign atom will be dissolved in the host, right? So that is what we need to find out. Okay. So now we will be talking about what is the criteria for the foreign atom because of there is a solid solution can be formed. Okay. So now let us talk about those points. So first is the atomic size. First is the atomic size. If the size difference between the host atom and the, or I can say the solvent and the solute, is within the 15% of their atomic radii, then only they both will accept each other. So what I am trying to say is that if the radius of the solvent and the radius of the solute, if this value is about 15%, then only there is a chance of formation of the solid solution. Okay, if that difference is greater than 15%, then both will not accept each other. Okay, both will not accept each other. So this is the first condition. Second condition, which already we have talked about, which is the sorry, point 2, that is we already talked about, that is the crystal structure. That is crystal structure. So I already said that, so solid solution is can be formed if the crystal structure of the solute and solvent are same. So here it means, what does it mean? It means the crystal structure of, sorry, crystal structure, crystal structure of both the solvent and solute has to be same. Okay, for example, if I am talking about, let's say, a substitutional solid solution which is formed by copper and nickel, right? Now, the so here I am talking about an example of it. So let's say I have copper and nickel which are forming a solid solution. Now, the solid solution is possible if now copper has a atomic radii of 0.128 nanometer, okay, whereas nickel has 0.125 nanometer. So if you calculate, okay, if you calculate their atomic size differences within the 15% limit condition, and also they both of them have FCC structure, FCC structure. So there is a probability that the copper and nickel will form a solid solution, right? The third criteria is the third criteria for solid solution formation is the third criteria is the electronegativity. Electro electronegativity. Okay, so the more the electropositive one element and the more electronegative the other, the greater the likelihood that they will form an intermetallic compound instead of a substitution solution. Okay, so it means that if the difference is large, electronegativity difference is large, they will form intermetallic instead of substitution. Okay, so what you want is that the electronegativity difference between them is less for to form a solid solution. Okay, so to form a solid solution, okay, difference in this electronegativity the difference in electronegativity should be small. Otherwise, what will happen? They will not form a solid solution, but they will form a intermetallics. Okay. The last point which we need to is the valency. Valence. Okay. Now, if all the other factors are okay, is maintained, a metal will have more of a tendency to dissolve another metal of higher valency than one is the lower valency. So what does it mean? It means higher valency of the for an atom is more preferable. So what does it mean? It means the valency of valency of solute atom valency sorry higher valency of solute atom is preferred. Okay, so these points are very important, right, for forming a solid solution, right? Now suppose if I am talking about an interstitial solid solution. So in case of interstitial solid solution, you know that for case of interstitials, the foreign atom or the solute atom will go and sit into the void of the host atom. Okay. So in this case, the concentration of the solute should be little low. I mean, because see what for the metallic atom which we are talking about, they have a very high atomic packing fraction, right? So for this packing fraction, atomic packing fraction is for high for metal, right? They have FCC structure or BC structure, and they have a very high atomic packing fraction, right? So it means they will have a very smaller size interstitials. Okay, so it means that the solute atom must have the size which is very small. Okay, so the size of the sorry, the size of the solute atom should have the size very small in compared to the host atom, right? And so therefore the concentration, as the space is very less, so the concentration for the uh, foreign atom will also be less, and in general that concentration of the solute should be within 10%. Okay, or probably less than 10% will be better. Now if I take an example, uh, for example, steel. Okay, steel. Steel is what? Steel is nothing but the carbon which is added with iron, right? And the maximum concentration of the carbon in the iron is about 2%. So iron is 98% and carbon is 2%. And still, remember, steel is an example of interstitial. So carbon atom will go and sit the the interstitial of the iron host, right? Why I'm saying so? Because the atomic radius for the carbon is about 0.071 nanometer, and radius of the iron is 0.124 nanometer. Okay, fine. So here you can see that that size difference is quite large in this case, and they will form an interstitials. They will form an interstitial. So copper steel is an example, very good example of uh, interstitial solid solution. Basically, we are talking about alloy, right? It is a very good alloy where you can see the corrosion resistance and the mechanical properties of steel is quite larger than the pure iron, right? If you are talking about pure iron, and the steel is much more better in corrosion resistance as well as the mechanical property. Okay, so that is what I just wanted to talk about in this part. Now next what we will talk about which is very important is that how this amount is decided and how this is presented. The amount, see, if you remember, I said this is percentage 98% and 2%. What? This is volume of the whole at the host, or the atomic percentage, or the mole percentage. So presenting this amount, right? What is the composition? So the amount in terms of material science or in terms of metallurgy, we call it the concentration or the composition. So it is, sometimes it become very important to express that concentration of the alloy or the composition of the alloy, okay, in a proper way. It can be a weight percent, it can be atomic percent, okay, or it can be a mole percent. So that is quite important, which we will be talking about next. So now we are going to talk about the specification of composition. Sorry. So now we will be talking about specification of composition. So it means we are now going to express the concentration of an alloy in terms of its constituent elements, right? And it can be presented in various ways. Mostly, the common way to specify composition is the weight percent and the atom percent. So now we are going to discuss the composition or the concentration. Composition of or concentration in terms of in terms of its constituent elements. Okay, that is what we are going to talk about. And I said that this, a common way of presenting it is a weight percent or atom percent. This is the two way of presenting it. That is what we are going to now talk about. Okay.